Hey everybody, Mr. Tan in here. Just want to try to make this quick video for today's asynchronous lesson, working through an example that's a little bit trickier. And if you get a shudder down your spine looking at this, I think that's natural, and oftentimes we all get that when, especially with all these tasks we're going to have to take and natural logs. I mean, I don't know about everyone else, but sometimes they just give me a shudder down my spine because I know they can be a bit tricky. But I think in this case, I'm hoping that it won't be too bad. So, as long as I attack it as Miss King taught me back in the day, with confidence and aggression here. So, let's see what I do know. I want to see if I can take this function, find increasing, decreasing intervals, find the locations of the relative maxima. Okay, well actually these two kind of go hand in hand, because if I find where it goes increasing and decreasing, or decreasing and increasing, it'll answer that question. And then I'll have to find, I'll find concavity and confirm with the SDT. Those kind of are both connected, the second derivative theorem. Okay, stay focused, don't get overwhelmed here, Mr. Tan, and let's get going. So the domain of this function, well, if I remember correctly, and I'm doing this in Algebra 2 right now, logarithmic functions cannot have an input less than 0. It can have an input of 0, and also here we can't have a we can't have an input of 0, I should say, my apologies, but nor could 0 be input because of the x in the denominator, because the denominator we can't divide by 0. So the domain would be from 0 to positive infinity. And we use parentheses because we can't include infinity, and we're not including 0. Okay, so first step in all these, find my critical points. Okay, and we talked about yesterday how the ones where the equals 0, we call those stationary points. And then also we have the points at which the first derivative doesn't exist. But to find the critical points, I'm going to have to find the first derivative so that I can set it equal to 0. So, low d high minus high d low. So, check your cheat sheet, but the natural log of x, its derivative is just 1 over x. Oh, that's going to work out nice. Low d high minus high d low. Well, d low is just 1, so I guess all over low squared. Okay, not too bad. Actually, one of the nicer quotient rules. X divided by x just going to leave me 1. 1 minus the natural log of x over x squared. Okie dokie, we got the derivative. So, and it looks as though this, the domain, if we think about now the domain of this, it's the same. I can't have a 0 for two reasons, because of the log and because I can't divide by 0. So I think this does exist, I should say with more confidence, everywhere on the domain of my original function f of x. So what we now need to do to find these critical points is set this equal to 0. So, because remember, this will allow us to find both of these questions once we have the critical points, bada bing, bada boom. So, set that equal to 0. So 1 minus the natural log of x over x squared equals 0. I can multiply both sides by x squared. 1 equals, add the natural log of x over, so saying e to the first equals x, or what we could think about is put e to the power of both sides. That undoes that. I just get e equals x, or x equals e. So that's a critical point there. Some of you might say, well, Mr. Tannen, don't we also have to set the denominator equal to 0 to find that where it wouldn't exist, and that would be at 0? But remember, that's not part of the domain, so that's why we're not considering it, which I was just thinking about myself. So what we could now think about is the first derivative theorem. Now that we've got the only critical point, I believe, we now know, well, we're not including 0, so we could kind of do this number line with that to show it's not included. We got the value, the constant e, and at e we know it's 0. So, at z we know it's the first derivative is 0, I should say, so it's stationary. So let's try doing some plugging in. So if I plug in, and let's try 1, for instance. 1 minus, well, if a log of 1, remember saying what power of e gives you 1, so it's the 0 power. So 1 over 1, there'll be positive here if we plug in, we tried 1, so it's increasing. And over here, we could try, for instance, e squared maybe. So e squared, just because it's nice to take the derivative of e, or sorry, the log. It's nice to take the natural log of e. So first I tried plugging in 1, so that gave me positive. Now let me try e squared here. Well, this is going to be the natural log of e squared is just 2, because it's saying what power of e gives you e squared. Well, the second power of e gives you e squared. 1 minus 2 is negative 1, but if we square e squared down here, we get e to the 4th. So we get negative 1 over e to the 4th, which is negative, so it's decreasing. So therefore, we found this to be an increasing to decreasing. We found a relative maximum, singular maximum, and we've also found the intervals on which it's increasing and decreasing. So this function, so f of x is increasing from 0 to e and decreasing from e to positive infinity. Interesting. And it has a relative maximum at e. Well, we got to find the output. Almost forgot that there. So let's go to my original function, which is ln of x. So what is the natural log of e over e? Natural log of e, so it's 1 over, is just at e, 1 over e. Wow, interesting. I can't wait to look at this graph at the end. Okay, so we did the first 2 steps. I know I'm scrolling like crazy. I'm trying to keep this under 15 minutes here. So we found increasing, decreasing intervals. We found there's only one relative maximum. Now let's find the concavity intervals. So if I'm to take the second derivative of this, ONG, so I get 1, that's my first derivative, 1 minus the natural log of x over x squared. I know to find concavity, let me switch colors, I have to find the second derivative. So let's go ahead and do that. We would have to do low d high minus low d high minus pi d low over low squared. Okay, let's see if we can simplify. Okay, that's nice. So that's just going to give me negative, cancel the square with that x, negative x, minus 1. Oops, maybe I'll distribute distribute that 2x first, so minus. I see what I could do here now. I could now just distribute that negative. But check this out. I could actually take away one of these powers, cancel out an x from all these terms, cancel out the fourth, and leave me with 3. So I just get -1 minus 2, which is -3, or 2 ln x minus 3 over x cubed. So that would be my second derivative. I know I spaced that out quite a bit. Sorry about that. Just did the quotient rule, did some algebra there. I know the algebra can be tricky. Come on, let's keep it rolling. Okie dokie. So first, let's see if that equals 0 anywhere on this. Well, the only place that this could is if the numerator equals 0, then this could equal 0. So we could set this equal to 0. Add 3, divide by 2, we get ln of x equals 3 halves. So actually x would equal, we put e to the power of both sides, we get x by itself. E to the 3 halves power would be a possible spot where the concavity could change. Alright, so we can see what the concavity is and then what that says about my function. So it's 0 there. So we could try just e and then e squared maybe, because those would be nice to plug in. So e, this will just give me 1, 2, it'll give me a negative, right, because 2 minus 3 would be negative. So it's concave down. Put an arrow down. E squared, it'll be 4 minus 3, right, because so it'll be positive, it'll be concave up. Is that right? Yep. Okay, so now we know the intervals of the concavity. Let me wrap this up. I know, so concave up from e to the 3 halves power to positive infinity, and it is concave down from 0 to, and then what else did I want to do here? Let's see, confirm the maxima with the SDT. So now we could also use this to see what the concavity, so if it's a maximum, it should be concave down, right? It should be getting less. So if it's going, so we said it had a maximum at E. So, yeah, because E, we just tested it, it's negative, so it's concave down. So confirmed F double prime of E is negative. Confirms. So again, the confirmation isn't super necessary, but it just shows how we could use the second derivative test if we had wanted to instead of the first, just to show you how it works. Confirms that it's a maximum at x equals e, which we found the output for there. Trying to wrap this up, I got 30 seconds. So to synthesize everything we found, increasing, decreasing, maximum, concave up, concave down, and that means, we know then if it changes from concave up to concave down, we know that this is a, it has an inflection point. at x equals 3/2. Oops, not 3/2, e to the 3/2. I could plug that in to get the output, but I just want to show you the graph here. So now if I were to look here I have the graph, and there's the maximum we found at e 1 over e. Kind of an interesting maximum there. And then here is where it changes from concave down to concave up, and it's got this horizontal asymptote as it approaches positive infinity. So this is kind of interesting that this is actually the inflection point is right there at that intersection, which is the x value of 3/2 and the maximum right there. So it would be hard for us to identify like this inflection point visually, but see the middle of the S as Kai points out for us. And this is concave down. Here is just slightly concave up all the way to infinity. Alright, I hope this video is helpful. It's definitely not going to probably be, well, just watch this and then I have a few Khan Academy questions for you to check out. Much love, everybody. Hope you have a nice day.